Okay, in this video we're gonna continue with the implementation of the Euler method using Octave. And what we're going to do now is we're going to solve this nonlinear first order differential equation, also known as the logistic equation for population decay. So if you watch the playlist, my playlist on differential equations, we actually solve this analytically step by step. So I have posted the link in the description so you can watch that in case you need to refresh your memory of how to solve differential equations analytically. But essentially this is a nonlinear equation because when you multiply this through, it gives you p squared, and because you have the function itself, the solution you're trying to find is not linear, then this becomes a nonlinear equation. So this is a little bit more complicated to solve, but it turns out that the analytical solution is just k over 1 plus a times e to the minus kt. And now obviously this a results is a result of integration, so it is an integration constant, and in order to find what it is we need to establish some initial condition. So let's say that the initial size of the population is 100 at time equals to 0. Then we get k over 1 plus a, and then we rearrange the equation to solve for a, so we get this expression right here. Now this is the analytical solution that we're going to test our numerical approximation against. And if we want to get the numerical finite difference equation using the Euler method, what we need to do is replace the first derivative by a finite difference approximation. So we're going to use the forward difference approximation, the same one that we used in the last video. So we're going to get p of I plus 1 minus pi over delta t equals to k. And now remember, everything else is going to have a subscript, so pi 1 minus pik, and at this point it is better just to expand this out. So we're going to solve for pi plus 1. That's the whole idea of this, setting up the equation like this. We're going to have pi plus k delta t pi minus delta t pi squared. So this is the finite difference equation that we're going to put inside a loop in our program, and then we're going to run that a whole bunch of times to get the numerical solution. So first of all, we need to choose some parameters. So let's make k equals to something like 0.5. Let's choose a step size like 0.01. And then we also need to select, well, our initial population we said was going to be 100. So this is basically it. Now what we're going to do is we're going to open up Octave, and I have already written a script for this, but I'll run you through the whole thing so you can see what we did here. So essentially what we did was we said, okay, so we're going to start off with our k value 0.5, delta t, which I just called dt here, 0.01. We have our initial population p0, that's 100. And now we're going to create a time vector that goes from 0 to 1 second. So basically our time is going to go from 0 to 1 seconds. Because as you will notice, once we plot the solution, this actually decreases very, very rapidly. So we can only see the change within a very small interval of time. So the next thing I did was, well, I calculated a based on this equation we just derived here, and I calculated the exact solution based on this equation. So I just plugged in all the values. Now you'll notice that I have this dot followed by the slash here, and the reason for that is that this quantity here, t is a vector, which means that exponential of a vector is another vector. So this whole thing in the denominator is going to be a vector. So if you're dividing a vector or a constant by another vector in Octave or MATLAB, what you need to do is to do that element-wise. So basically you're dividing this by each element of that vector. You need to put a dot in front of your operational kind of symbol. So this will give you the exact solution for this interval of time. And now the next thing is we are going to create a empty vector p of zeros that is going to contain the numerical solution, and it is going to have the same length as t, and we're going to assign the initial value to it by saying p1, which is the first element in this array, and it is going to be equal to p0 or p0. Now inside the loop we're going to put this finite difference equation So you can see that I have written it here in the same manner. So we have dt times k times pi, and then we have pi squared here, and that's going to solve for every value. And remember that our loop is going to go from I equals to 1 to I equals to length of t minus 1. And the reason we have to subtract this 1 here is because we have I plus 1 here. So we want the vectors to be the same length, essentially. And down here, I have just written the same thing that we did in the last video. Basically, just a plot. I added some legend to differentiate which plot is which, some labels and all that. So this should all work, and let's see what our solution is going to look like. Okay, so we have the solution here, and we can clearly see that, oh, well, our Euler solution is very, very inaccurate. I mean, look at this. It goes down very abruptly, and then it just goes off like that. So it's way off the exact solution here. So this means that our step size was probably not good enough in this case, even though this proved to be quite good in the previous example. But this is just a consequence of having a nonlinear differential equation. When you have nonlinear differential equations, your step size is very critical. And you can see that even for 0.01, which would normally work for a linear differential equation, here it's just completely useless. So let's reduce this further and see what we get. So instead of that, let's try 0.001. And that should change this significantly. I don't know if... Let's run it again and see. Okay, that's much better. So let's increase the window size here. Okay, so it's a little bit hard to see, to tell the difference, because obviously this is so... It's very close now. So you can see that we decrease our step size by an order of magnitude of 10, and immediately our Euler solution now approximates the exact solution very, very well. And this is actually a really nice curve here. Now, obviously, if we wanted to quantify, if we wanted to see how much it differs, we would plot the relative error. So we can do that here. We can write another equation. We can write, say, so before the figure, I just want to put all the figures down below. So let's say error, and we're going to use the relative error again. So absolute value of the following. So we're going to do p exact, and remember we need to use this, minus p numerical over p exact. And because we're dividing between vectors, we need to use this dot slash notation. And I believe this should be good enough. So let's try and see what... Let's just write figure 2. And we're going to have plot t against the error. Let's add an x label. So x label time in seconds, y label relative error percentage, and then no title. That should be good enough. So let's see what we get from this. Okay, not sure why that is, but okay, apparently it was still running. So this is our step size, and we can see, okay, so this is a relative error, and it is no longer linear. So it means that once it gets to this point, it actually approximates the solution quite well. So it depends, it really depends on the type of equation you're solving, but you can clearly see that this is really good. So it only actually goes off when it gets to this point, but then after that it starts to converge to the exact solution again. So this is actually really good. We can see that the relative error percentage is less than 0.04%, which is quite a good approximation. I mean, it really depends on how accurate you want to get, but a general rule of thumb for engineering and science is that anything below 0.1% error is really good and is quite useful. So I would say at this point this is probably good enough for us. So this is just to show you how you implement the Euler method for cases in which you might not have a linear equation. You can also apply it to nonlinear differential equations. All you need to do really is just solve for the first derivative, then change it by a finite difference equation, and then just get the finite equation put into a loop, and then just loop over a whole bunch of numbers and you get your numerical solution. Now obviously you need to make sure that your step size is small enough. In this case we found out that for this nonlinear differential equation, this step size was not good enough because we got that abrupt curve that didn't even look smooth. So obviously you just need to play around with step size to see if there's any improvement. And you should always see convergence. So if you decrease the step size, you should see the relative error decrease significantly, and you should see your numerical solution approximate the exact solution. Now obviously the whole point of using numerical methods is to solve problems that cannot be solved analytically. So in that case, what you would seek, how you would compare whether your solution is accurate enough, you would try a whole bunch of different step sizes, and then you would look for convergence until you see that by decreasing the step size further, the solution doesn't seem to change much. So that's the point in which you know that your solution is converging. That doesn't necessarily mean it's correct or more accurate, but it is a starting point that tells you you're on the right track. And we'll talk more about convergence a little later on, but for now we're going to focus on the Euler method. And in the next video we're going to learn how to solve a second order differential equation using the Euler method.